So thus far in this class, we've been considering our hydraulic fluid as incompressible, and we've said that's a reasonable approximation for most of what we've been doing. Now we'll start to explore when the fluid is compressible or when we consider the compressibility effects to be important in our system. So I've mentioned that it's compressible, and just the bulk fluid itself is slightly compressible, but when it becomes much more compressible is when we have entrained air in the fluid. In other words, if we are agitating this and we get little air bubbles in here, then those air bubbles become very spongy and add to the compressibility. So we describe the fluid compressibility through the bulk modulus. That's how we define it. And I have it here, and a way you can think about the bulk modulus is really what is the pressure required to cause a given volume of fluid to change volume by a certain amount. So lots of derivatives here. And a very nice thing about this equation is we can use it now to model the pressure in a given volume dynamically, given an input flow rate, an output flow rate, and perhaps a moving wall or a moving volume. So this is a very useful equation for a variety of situations. To give you a feeling of what the values are of a bulk modulus, well, first of all, think about the units here. Notice that the denominator of the bulk modulus equation is unitless, dV by V. So the numerator has to be the same as, or I'm sorry, the bulk modulus has to be the same as the numerator or pressure. So we're in units of pressure here. And typically hydraulic oils are 1.5 to 1.9 gigapascals. Water is typically about 2.2 gigapascals. And again, this changes greatly with the amount of entrained air. It's also a function of pressure. So to give you a feeling what that looks like, here's a plot of the bulk modulus as a function on the x-axis of pressure, and then the different curves are for different amounts of entrained air. So when I say that hydraulic oil might have 1.6 gigapascals bulk modulus, that is what it plateaus to. But as we add air to that and as we decrease the pressure, the bulk modulus drops. And so to do a really good job of modeling this, we would ideally have a pressure-dependent and entrained air ratio-dependent bulk modulus term. So just to give you a feeling of how spongy is hydraulic fluid, well, let me throw out some numbers here. So if I rewrite this as delta V over V, and this is equal to a minus delta P over the bulk modulus. Let me throw out some common numbers, maybe for a 5,000 psi system, which would be 35 megapascals. So I've got minus 35 MPa, so that's 10 to the 6th, divided by, let's say, 1.6 gigapascals, 10 to the 9th. I'm ending up with compressibility of right around 2.2%, so minus 2.2%. So just to give you a feeling, you know, our oils that we're dealing with are usually 1 to 3, maybe 5% compressible, depending on how much air is in that oil. So often a reasonable assumption that it's incompressible, but in some cases this does become important. Now, before I move on, let me just mention the sign here. Notice that we have a negative sign in the definition of the bulk modulus. This is just due to how we define a change in volume. So notice that a dV is considered a reduction in volume. So that's a little bit arbitrary, and we can take care of that later. So I was mentioning, where is this important? So first of all, it's important for systems where we need to do very precise positioning. So consider that I have a hydraulic cylinder, and I'm trying to very precisely position this end effector, and perhaps there's a lot of mass attached to this. And I don't want to have much compliance to my system. I want it to be very stiff. And that can be an issue if our fluid is compressible, especially if there's a lot of air trapped in the system. So we have to be aware of that. Second, I'll talk about more in just a moment, is resonance of the system. The fact that we can get dynamic resonances of a square root of K over M sort of term, and having that influence our system, especially with high frequency systems. Often servo-hydraulic systems that are running at very high frequencies get into the resonant frequency of the hydraulics. And then compressible energy losses. And you might say, well, what do you mean by that? If we look at a hydraulic pump, as we were talking about before, and we were looking at the piston-cylinder interface, now in that piston cylinder, we have, when the piston comes up to the top dead center position, we still have some dead volume in the chamber. Well, that fluid was compressed previously, and now we're going to open a valve to tank pressure. And so the energy that went into compressing that fluid is exhausted to tank, and then we're going to do that cycle after cycle. And this is happening, you know, for 3,600 RPMs. This is happening 60 times a second. So it ends up being a significant amount of energy loss over time if we have a large amount of dead volume in our cylinder. So again, different areas where this small amount of compressibility does add up over time and does become important. So let me talk a little bit more about resonance as one of the key areas where this becomes important. So think about a long, slender cylinder, something like this, relatively small diameter, long stroke. And I'm going to just do an analysis of what the resonance frequency or what the natural frequency of this system is. I'm going to simplify this ever so slightly, first of all by saying that my piston hub length is basically minuscule, and so the length of the oil column on one side plus the other oil column length is the total length of the cylinder. Second, I'm going to say that my piston rod is very small, or that I have a double-ended cylinder and that the area on each side is the same. So just some simplifications to make my math a little bit easier. So I'm going to start off with just the bulk modulus equation, and notice that because my areas are the same, I can substitute in the lengths instead of the volumes on each side for the delta V and the V. And I'm substituting delta F over A for delta P. Now, I recognize if I'm going to treat this system as a spring, I can write a traditional spring equation, just F is equal to K times X, or delta X. In this case, our X is just the length of the system, so delta L in this case. So now let me substitute this in. So I'll solve for K, and this will just be delta F over L, and this is now the bulk modulus times the area divided by the length. Notice that I did remove my negative sign here because, again, it's an arbitrary decision of what direction is a positive delta L. So I'm removing that right now because it'll end up under a square root, and that's why I've removed it here. Now I'm going to consider that I've got this compressible oil on one side of the piston hub and also on the other side of the piston hub. So now I have these two springs that are in series, and so I can write them as an equivalent spring. So I'll take these two, write them as an equivalent spring, and I basically just add them up. So as I add them up, I get this term here that's on the bottom for the spring rate of my system. So that's a spring rate. All right, now we have a mass that I'm saying is attached to the end of this piston rod. So if I've got a mass and a spring rate, now I can write my equation for the natural frequency of the system and then use that for further analysis. So now I have this form for my resonant frequency, and we might say, well, where is it going to be the worst case? Is it going to be all the way at one end? Is it going to be a quarter of the way? Is it going to be centered? Where is it? Well, recognize if I move the piston to one end, now I have a very stiff spring on one side, and so that drives up my spring rate. But if I end up with the piston hub in the dead center, that happens to be the case where we have the lowest natural frequency, or the worst operation, if you will, when L1 is equal to L2. And in that case, the natural frequency simplifies quite a bit, and we're left with this equation right here, just 2 times the radical of the bulk modulus times the area divided by L over M. So again, notice that just like our spring rate equation, when we get to this natural frequency equation, the slenderness ratio, this A over L, becomes the driving parameter for the resonant frequency. So let's now do an example calculation for this hydraulic cylinder here. Now, let me say I'm going to add a chunk of mass onto the end of this, 10 kilograms for say, and I've measured the cross-sectional area of it, 1.2 times 10 to the minus 4th meters squared, and the length of the stroke here is 20 centimeters. So let me take those numbers and plug this into the equation that I have here, and now I've got 2 times a bulk modulus of maybe 1.6 gigapascals multiplied by the area of 1.2 times 10 to the minus 4th meters squared divided by the length of 0.2 meters and the mass of 10 kilograms. And then I'll take the square root of all of that. And so when I compute this natural frequency, I end up getting somewhere right around 619 radians per second. And if I convert this into hertz, this ends up being about 68 or 98 hertz, I'm sorry. So about 100 hertz natural frequency for this system. When we get into servo-hydraulic systems, we're going to find that that really is within the range of what many hydraulic systems operate at. Sometimes they get up into a couple of 100 hertz. Very rarely we'll get into 1,000 hertz. So we are getting into the resonant frequency of some hydraulic systems, so we have to be careful how we're operating when we get to those regions, and there's some special things that we can do. One thing that I have neglected with this calculation is the additional hydraulic oil that would be between the valve and the cylinder itself. So there would be additional compressibility, which would further lower this natural frequency. So in some situations, a long, slender cylinder like this, we can have fairly low natural frequencies. So in this video, we've talked about the compressibility of hydraulic oils and how we model that with the bulk modulus equation, and then talked about a few specific cases where it's important, including this case of resonance.